Okay. Can you all hear me? Okay. So yeah, I'll be talking about iOS and Android application security. And basically, so the mobile application market has exploded over the last 2 years. And there's been an insane amount of demand for security reviews of iOS applications and Android applications in about the last year, year and a half. At the time, about a year and a half ago, there was very, very little published about this stuff. This has changed in recent months. There was a lot of stuff done at Black Hat this year and DEF CON. So we're getting there little by little, but there's still plenty of stuff to be looking at. I've done over a dozen of mobile application security reviews in the last year. And basically, this entire presentation this is all the stuff I've learned over the last year. Originally, I started off looking at iOS applications because that was asked of me. And then later on, a couple of months ago, I started looking at some Android applications. And what I found is that there are a lot of similarities between features in iOS apps and Android apps. And so at the same time, there's a lot of similarities between potential security issues in iOS apps and Android apps. And so basically, this talk will be sort of a comparison between the two, with the main focus on iOS, but there's Android stuff sprinkled on top. So basically, what I'll be talking about is I'll give a brief overview of the application environment and then go into sort of the issues I've seen with transport security, IPC, web views, images, HTTP connections, format string bugs, binding protocol handling, picture reversals, XML handling, SQL injection, and then some type confusion stuff. So the application environment for iOS, they're all native apps. They're all written in Objective-C. iOS itself is a port of macOS. It's basically macOS on the ARM CPU, and the GUI's changed a little bit, and there's different objects for the GUI stuff. But in essence, it's basically OS X on the ARM CPU. All the apps are in Objective-C, or most of the apps are in Objective-C. Objective-C is known as to be a strict C superset, which means all valid C code is valid Objective-C code. Objective-C they bolted classes on top of C and then added some weird syntax. But they do have a bunch of classes that take care of the low-level stuff, meaning that buffer overflows and like are much less likely. Android is slightly different. They use a modified, or depending upon your point of view, a mutilated version of Linux. The applications for Android are mostly written in Java. They don't use the Java VM. They have their own VM called Dalvik, which is source compatible but not binary compatible. They don't have jar files. They've got what's called DEX files. And then Android also comes with what's called NDK, which is the native development kit. And that allows you to write C and C++ code for Android applications. This feature was mostly introduced to port stuff from desktop and server apps to Android apps. And so there's very trivial to use interfaces from Java to C and C++ for Android applications. So the first thing I'll be looking at or talking about is transport security. Turns out there's a large number of applications that run on iOS that you would want to use some kind of transportation security, online banking, online trading, all sorts of stuff where you don't want your data to just leak out in the clear. Most of these apps, they will end up using SSL because it's the easiest thing to do, and the SSL stuff is just embedded in the APIs, and you don't have to do anything really. This usually happens by using HTTPS links, and you end up using NSURL requests and NSURL connections, and just using those classes, the SSL sort of happens for you. The API uses a default set of SSL ciphers, which if you sniff kind of looks like this. This is the initial client hello handshake. And if you take a little bit of a closer look, you see there's a whole bunch of cipher suits in there that you really don't want to be using, including DES, export ciphers are 40-bit RC4, 40-bit DES, so that kind of stuff, which you really, really don't want to be using. But it's there, it's on by default, and you can't turn it off. And when I say you can't turn it off, I mean you can't turn it off with documented APIs. There are undocumented APIs you can use to turn off these weak ciphers, but if you use them, your app will not pass the App Store, it'll get rejected. And what's really funny about this is that it's documented, that it's not documented. So there's a secure application programming guide from Apple, and that one says for the secure transport APIs, it says The Secure Transfer Programming Interface is not available on iOS. Use the CF Networking Programming Interface instead, which may be a great library. It doesn't support, it doesn't have support to change cipher suits. So you're kind of hosed on that one. Basically, the APIs aren't granular enough. They don't allow you to set cipher suits. You can't fix it at all. If you try to use the undocumented APIs anyway, Apple will boot you from the App Store. The only thing you can really try to do is basically not use Apple's APIs and use an open source SSL library and use that one instead. And there's a couple that are actually built for embedded use, such as yet another SSL implementation and Matrix SSL. So I would, if you're building iOS apps and you need SSL, I would recommend you use these two libraries instead of the native one. But you know, it can get worse. So documentation thing I quoted earlier mentioned CF Network, and CF Network, as far as I understand, doesn't allow setting cipher suits, but it allows you to set a few other things. It allows you to say we use expired certs. It allows any root. It allows not validated certificate change. So you can do all these things. And this is kind of what it looks like. So if you're writing the objective code, you set these few bits, and then all of a sudden you just allow anything in. Here's the good news. It's not on by default. It takes a little bit of work for a developer to screw this up, but it isn't unthinkable. In fact, I was on one particular engagement where I saw this stuff and I'm like, wait, what are you guys doing? And they're like, oh crap, that's supposed to be debug code and we're about to ship this stuff. So it happens, it's just rare and not on by default. On the Android side, things are almost as bad. These are the set of default ciphers, which are even worse. It's a longer list than the iOS one. It's basically all the desk crap and all the export stuff. It gets a little bit better in that Java actually comes with a set of APIs to change the cipher suits. The ones I just gave you were the default. You can't actually change this shit. If you use the set-enabled cipher suits API on SSL sockets, you can turn them off and you can specify which ones you do want. And it kind of looks like this. So you get a socket, you create an SSL socket, you say only this particular cipher suit do I want to use. Then you create a context, and from that context you create a factory, and from that factory you get an SSL socket. And on that SSL socket, you say it's client mode, and then you say set enabled cipher suit, and then you use this set of strings here. And then when you use that socket, it will only support RSA with AES on 28-bit. So that's obviously significantly better than all this export crap. So that's what, if you're doing Android app development, that's what you should be doing. Don't rely on the default, it's terrible. Next one is basically the interprocess communication, where you want to have apps talk to each other. And this is kind of a problem on iOS and iPhone and iPad, because by design, iOS apps aren't allowed to talk to each other. This was not by accident. This was very much designed to be that way, which I guess you would arguably could say is a good security feature. But sometimes your developers will actually want to have apps talk to each other, which is kind of a problem because now you have no interfaces for that. So developers are like, well, let's try and find a way around it. And they start looking at some of the stuff and they said, oh, you have these URL handlers you can register. I think we can use those to have our apps talk to each other. Initially, that was a hack which passed the App Store, and at some point, Apple embraced it and said, okay, that's now the supported way to do IPC between applications. And this was invented by a company called Mobile Orchard a couple of years ago, and it is now an allowed and developer documented feature on Apple's developer website. And the way it works, basically, you register your URL handler and you serialize and deserialize arguments over the URL handler, and then when you call that URL handler, iOS will see, oh, this URL handler is this application, and sends it off to that application. And basically, if you want to do that in your application, you've got to fill out this info.plist, and you got to say, this is my URL scheme, and this is, so in this case, it would be called the my protocol, would be, my protocol : // and that would be the URL handler. You have to define a callback for that, which is the handle open URL method right here. And that one basically gets called if you were to fire up the my protocol handler. Problem with this is that any web page can call it too. If you surf to a website with mobile Safari, then all of a sudden that website ends up calling your application, and fires up this application, which opens up this interface, which is only intended to be IPC between apps. So that's kind of an unintended consequence right there. But it gets worse. I mean, it's nice, I guess, from an attack point of view that a browser can do that. But in this case, you still have to get someone to open up their iPhone and go to my website, and they have to go to the website, and then only then can you do it. And so I started looking at this, and I said, well, maybe there's a way to just get the iPhone to go to my website without having someone pull out their iPhone and go and surf to a web page. And it turns out there is a way to do it. As of iOS 3, they have this cool feature called Wi-Fi hotspot. And what that thing does is, this stuff is on by default. And as soon as you connect to a Wi-Fi network, the very first thing iOS does is it goes out to www.apple.com. And if it gets a 200 response back, it says, that's fine, I have a good network connection. But if it gets a 302 back, which is an HTTP redirect, it says, oh, this must be a Wi-Fi hotspot. Why don't I bring up the browser and let you log in? And it kind of looks like this, which is absolutely perfect because we could totally abuse this. Basically, if you're on the same LAN with someone, you knock them off the wireless network, and when they come back on the network, you spoof a 302, and it goes to your page, and your page says, why don't you fire up this application for which I have an exploit? And it just all happens automatically. And this stuff is on by default. On iOS 4 and higher, you can turn it off. On iOS 3, you can't turn it off. So as I said earlier, Apple sort of embraced this IPC mechanism, and they said, we'll try to make it easier for developers. And what they did is they came up with a new API. Instead of handle OpenURL, they made OpenURL. And what OpenURL does is it allows you to, it passes you a source application. It's an application ID, and then it also passes over arguments. So you don't have to serialize stuff anymore. iOS will serialize stuff and deserialize stuff for you. So it's actually a lot better, and if you're developing iOS apps, and you want to be using URLs for IPC, you should be using OpenURL and not handle OpenURL. Because the great thing is you get a source application, so you can build a whitelist or blacklist of apps that you want to talk to that you don't want to talk to. So now if you implement OpenURL, you can say, oh, you're coming from the browser? There's no way I'm taking your data. So obviously OpenURL is a much, much better API, more elegantly designed. It's easier to use. You don't have to serialize all of this crap. And there's an application ID, so you can build whitelists or blacklists. If you're doing iOS apps, I'd recommend using this one. IPC on Android is significantly different, but it's still kind of IPC. The difference is that on Android, every application runs with its own UID. And so there are some mechanisms put in place so apps can talk to each other over what was supposed to be well-defined interfaces. And what's better about this is that this stuff can't be called from browser. Only apps on local phone can talk to each other. However, with IPC, you have to define what's called activities, and the idea is that you basically expose the functionality, and then other apps can call to that particular functionality or that particular method, and do this kind of stuff. Turns out this stuff is highly vulnerable to repurposing attacks because a lot of these people that develop mobile apps, they'll be like, oh, we have this cool feature which we can now export to phones, and they wouldn't think for a second about security. And so I think, for example, Skype had one where any app could arbitrarily go into Skype and say, call this number. I've looked at a number of Android apps where a bunch of these apps, they would talk to a certain backend with credentials stored in that app, and any app could talk to that particular app and say, why don't you upload this document or download this document and use your credentials. And that totally worked. So this IPC stuff is vulnerable to repurposing attacks if you don't know what you're doing, if you don't care about security. But it's kind of interesting because, so you define these entry points in what's called the Android manifest XML file. And the way it works is you declare what's called an activity. So you have an application tag, and inside the activity, you define your activity, and that basically you point to, this particular activity I want to do in this particular Java file. Now you're supposed to set an exported attribute on this activity tag. And that basically says, is it exported or not? Except it's not quite that simple. The documentation is quite confusing. And this is only like a small bit. There's a gazillion more things you actually should know about whether or not it's exported or not. And so one of the things they say is the default value of an activity depends on set so-and-so and so. So default may be either true or not, depending on other tags you set. Some of this stuff is basically, if in the absence of any filter, then the default activity is off. But if there's any kind of filter put in place, then the activity is on. Unless, you set permission so-and-so, and then none of this holds true. And there's a gazillion other of these tiny little rules. This IPC stuff is very complicated, very confusing. No one really knows if stuff's exposed or not. The only really way to figure out if shit's exposed is to compile the app, run it, and see if it's exposed or not. Besides that, it's really just a crapshoot. So the next bit I looked at this is called UI web views. And UI web views are basically allow you to embed a browser in your mobile application. And on iOS, people have sort of used it for two different things. First, people have actually used it not as a browser, but as a GUI element. Because using some of the GUI objects in iOS is kind of a pain. And so basically people said, you know what, I can build up a GUI in HTML. It's 100 times easier. I'll just render it, and that'll be my GUI. And obviously the second thing people would do is they would use UI web views as actual embedded browsers. So let's talk about using this stuff as a GUI. This stuff is vulnerable to attack. If users can get their data in there unescaped, obviously leads to cross-site scripting. And now you go, cross-site scripting, this stuff is actually kind of cool. By default, there's no bridge from JavaScript to Objective-C. But it turns out there's a whole bunch of iOS developers that said, if I'm going to be using this stuff as a GUI, I need to be able to call back to Objective-C to say update this and update that and so and so. And so people said, well, we need to be able to have a bridge between our JavaScript and Objective-C. And so the way they did that is there's a callback, which is called should start loading with request. And if you implement that one, then you can do all your bridging logic in there. And that URL can do anything the developer wants it to do. And usually what happens is, you marshal some arguments back and forth. And people would put stuff in the GUI metadata, in the HTML they're trying to build up for the GUI. They would put indexes and pointers and all sorts of metadata in there that they consider trusted. Except if you got cross-site scripting, none of this stuff is trusted anymore. And they would take this data back in Objective-C through JavaScript, and they wouldn't validate any of this stuff. They would take a pointer and read from it, or write to it, and all this stuff, they would just trust it. However, it gets worse. Sometimes people would like to expose arbitrary Objective-C methods to JavaScript, and so they would build this Objective-C bridge, and they would serialize arguments and deserialize arguments and method names. And it kind of looks like this. And this is an example of what you shouldn't be doing. And so I found this stuff. Basically, a lot of this iOS development happens through like online developer communities. And a couple of these basically say, oh, this is what you should be doing. And so people end up just copy-pasting this code one-to-one. And so this happens to be a fair number of iOS applications. And the way it works is they take over the arguments in the function name, and then they say perform selector, which is basically just called this function pointer. And they do runtime resolution of the function name or method name, and then they just call it. So if you have an iOS application that uses this thing, and it's vulnerable to cross-site scripting, that's arbitrary code execution. That's the part where people want to use as a GUI. Now, if you want to use it as a simple browser, it's not as bad, but it's not as good as you would think it is. Because the Safari mobile browser actually does a lot more than just render HTML pages. It can render a large number of file formats. So it can't do Flash, but it'll do Excel, Keynote, Numbers, Pages, PDF, PowerPoint, Word, Zip, RTF, and a whole bunch of other file formats. There's a long list in there. The list is not, there's a longer list. I just put the ones in there that I thought were funny and interesting. Obviously, we know these file formats are enormously difficult to parse. No one has ever written an Excel file format parser and not made at least 10 bugs. So we know that stuff's bad. We know there's going to be buffer overflows in there. But it's there. It's on by default. And it just happens. There's no pop-up. you point Mobile Safari or UI WebFuse to a .doc file, it'll just render it. And it won't just render it, it'll actually take the file, convert it to HTML, and render it in the current DOM. Which is interesting because, there might be some cross-site scripting stuff in there as well. This stuff is on by default. There's absolutely no way to turn it off. I looked, I tried, there's no way to turn it off. This stuff will handle document files and pages and RTF and zip, and it'll just do it, can't turn it off. Just a few other things, such as it interprets the telephone URL handler. That one you can't turn off, and if you don't need him, just turn it off, right? So, as I said, there's no way, I don't know of any way to turn it off. The only mitigation I know is to not use UI WebFuse, and to basically say, listen, if you want to do a web browser, we're not going to use WebFuse, we're just going to call out to Mobile Safari. And if someone's got a bug for a word bug, let them exploit Mobile Safari and not my app. It's not really a good fix, but it's the best I can come up with. On Android, it's kind of similar. They have this thing called WebView, which is exactly the same thing. It can be vulnerable to cross-site scripting if people aren't careful. They have bridges. There's a way to do bridges from Java to JavaScript. And this is documented. They call it Add JavaScript Interface. And if you look at the documentation, there's actually a really cute note in there which says, be very careful because there's some security concerns here. So it's quite clear to Android guys when they started developing their APIs. They sat down, they cared a little bit about security, and they started documenting this stuff. And they said, if you want to build this bridge, be very, very careful. But in essence, WebFuse, UI WebFuse, they expose very similar functionality. UI images is sort of a similar class for the iOS. And what UI image does is it's sort of a container class which can hold a whole bunch of different file formats. And you just point it at something and it'll just take it, figure out which file format it is, and render it. This is a non-exclusive list of, a non-exhaustive list of the formats it supports. There's TIFF, JPEG, and PNG, and bitmap, and icons, and cursors, and so on. And then there's also embedded formats inside these image formats, such as EXIF and ICC profiles. And all of this stuff is all very hard to parse binary file formats, which again, we know are incredibly hard to parse, and chances are Apple screwed it up somewhere in their implementation, probably multiple times for multiple file formats. And it's the same thing as before. There's no way to turn it off. There's no way to say, I'm going to use an UI image, but I only want to render a bitmap file. If you hand me a JPEG file, I'm going to reject it. There's no way to do it. There are, however, two possible workarounds. The first one is to use what's called the core graphics APIs, which are significantly more low-level than usage of UI image. They're also kind of hard to use. But the good thing with core graphics APIs is that they do have a different set of APIs for every file format. So if you use the core graphics APIs, you can use the, just use it. If you only use the JPEG ones, if you try to use a bitmap in there, it'll barf and say, I'm not taking this shit. And the good thing is, once you do core graphics, you can get a handle back to your core graphics image, and you can pass that handle off to UI image. So you can build sort of a step on top of UI image to sort of use core graphics first. The second one is to say that if you decide not to do core graphics, is to say that just before you hand stuff off to UI image, is to look at this binary blob and look for the file signatures. And what's interesting about pretty much any image file format is that they all have a signature in there. And so, the PNG one kind of looks like this, and then the JPEG one looks like this, and the bitmap one looks like that. And so what you can do is before you hand this data off to UI image, you look at the stuff and say, I want to look at a PNG file. If it doesn't start with 137.80 and so forth, then it's not a PNG file, and I'm going to reject it. If it is a PNG file, then obviously you can pass it on to UI image, and hope no one has any PNG exploits for UI image. The next thing that is HTTP header injection. It's not mobile specific, or it's not iOS specific, it's not Android specific, but it's incredibly common in mobile apps. And most of this is basically when you're interacting with web services and you send SOAP or JSON or whatnot over HTTP interfaces. HTTP header injection happens when potentially attacker-controlled data is put in an HTTP header value, and the next line isn't escaped. Incredibly common. This is a very trivial example where somebody's trying to upload a file, basically. And then if an attacker were to have control over this file name, then header injection would occur. iOS has specific APIs to append headers to NS URL requests. These are called add value and set value. These APIs are actually not bad. They're not vulnerable to injection. When they see next lines, they'll detect it. They will fail silently, so they won't tell you, and it's not documented that they fail silently. So you do end up with a bug there. It's just not a security bug. It's a functionality bug. Someone at Apple should document the stuff, but I'm kind of okay with this because there's no security bug when you properly use these APIs. Android, not quite as good. This is one of the few areas where Android comes out worse in my comparison or things I've looked at, where Android comes out way worse than iOS. Android actually has a number of APIs to do HTTP handling from the client side. The most common one I've seen is using the Apache HTTP components, and this is where you include the org.apache HTTP. And so that one has a set of APIs too. It's called add header. Add header is incredibly low level. It does not encode anything. It takes your data and just puts it right in the request. It doesn't validate anything. It doesn't encode anything. It doesn't do anything. It's completely vulnerable to injection. And so I have like a little test app for this stuff. And so if you build up the stuff and you do a request add header and you set a header and then you add injection in there, and then when you compile this app and you run it, it kind of looks like this. No idea if you can actually read the stuff, but the white is the client and the black and green is sort of the fake server where I use Netcat. And then when I run the client test app and it prints blah and then it has this massive stack trace. But then if you look from the server side, you get the GET request and the host header and the connection header and the user agent header and then header 1 and then injection, the injected header basically. So it totally works. I would hope at some point, whoever owns the Apache Commons will do something about it. But currently this happens, and if you're not careful writing Android apps, people could use this stuff to send out arbitrary HTTP requests with whoever's running the app with that guy's credentials. What's interesting about iOS and the iOS application environment is that, as I said earlier, everything uses Objective-C, which is native code. And as I said earlier, if you stick to the Objective-C syntax and you stick to their classes, you're pretty much safe from most buffer overflows. However, most of these classes come with their own format functions, and they are vulnerable to format string bugs. I've looked at least a dozen iPhone apps over the last year. With the exception of one, every single one I've seen has had at least one format string bug. The reason why, I think, is because most people that end up writing iOS apps don't come from a C background. It seems most of these people used to be web developers, and they come from writing PHP code or Java or JavaScript or ABAP or whatnot, and they don't know what format functions are, and even if they know, they would have no clue as to how bad it is to abuse format functions. And so basically, these are the Objective-C specific format functions where, if used incorrectly, these things will lead to arbitrary code execution. So NSLogin, string width format, init format, append format, and so forth and so forth. Objective-C, as I said earlier, is a superset of C, which means if you start using the C format functions, those are vulnerable to format string bugs as well, which obviously we already know, printf, snprintf, fprintf, those kind of APIs. Objective-C is slightly different though, because so I don't know if you actually end up, if you've ever written a format string exploit, the gist of it is basically that you use the %n specifier to write data to arbitrary memory locations. I don't know, maybe good or bad thing about Objective-C format functions is that they don't support %n specifier. And so when I found this stuff, I was like, well, gee, that kind of sucks. So that means you can only leak data out or maybe make the app crash, but you can't actually get code execution out of it. And then I started looking at the man page for Objective-C format functions. And I come across this thing, a new format specifier called %@. And the %@ documentation basically says the following. Objective-C object, printed as the string returned by description with local method, if available, or description method otherwise. When you see that, I was like, jackpot. You get to call arbitrary function pointers on an NS object that are on the stack. It's not quite that easy. You have to jump through a couple of hoops. And so I made a little test app to start playing with the stuff. And later on, if you end up seeing x86 assembly instead of ARM assembly, you'd be looking at this correctly. I tested this stuff in the emulator. I haven't gotten around yet to doing it in ARM, but I know the functionality is quite similar. It's just, x86 instructions right now, not ARM yet. But this is basically a small test app that I made, which basically takes a string as an argument. This is a clear format string bug right here, where user attacker control data is passed as format string bug to the nslog function, and then basically after that it just returns. So if you run that thing in GDB, and the first 4 bytes are B, 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 and then %x to pop crap from the stack, and then %@. It crashes, and what you see is it crashes on the address 0x62626282, which is pretty close to B, 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 B. So clearly it popped this pointer from the stack, and it's trying to reference it, and it's dying right there. And it's dying in this method, in this function called Objective-C message send +23. So clearly it died there. It's trying to pop an NS object pointer from the stack. And so basically, let's see what Objective-C message send do, what it does, how it handles this data, and how we can get code execution from there. So first thing it does is it takes your pointer from the stack, and so basically it puts it in this AX register, and AX basically holds your pointer to NS object pointer. And then they get another pointer at that one, and basically that gives you another pointer to NS object, which is now stored in the D register. This is basically where we crashed. Basically, they tried to dereference this pointer plus hex 20, and they tried to read a value out of it. This is the actual pointer in this object, and this is why we saw the 0x62626282, because of the addition of the 20 to it. Basically, so in order to exploit this stuff, that pointer needs to be changed, and it needs to be changed, and it needs to be point to a valid piece of memory where you control the content, and that content is going to be the content of an NS object. And then that value is another pointer which is stored in the EDI register. And there's an AND mask done on top of that stuff, and then, which is sort of this gibberish stuff here. And then basically that mask is used to compute an address that will get dereferenced. When I started looking at the stuff and trying to build an exploit, what I did was if you make the mask 0, nothing gets taken off, and you just get a valid pointer. So basically that pointer gets added, 8 is added to it, and then it gets put in the A register. And this is yet another pointer. And the reason why we know that stuff's a pointer is because the very first thing that happens is there's a check for null. If the pointer's null, then do so and so. Once we get there, things actually get interesting because it points to another structure, and I'm sure this isn't the right name, it's just what I figured it might be. And this structure contains 3 things. It contains a magic value, it contains some dummy value, of which I have no idea what it is, and it contains the actual function pointer. Turns out, what I later found out is that this magic value is actually really a pointer. And it's a pointer which needs to point to a valid NS object. It never gets dereferenced, but they need to make sure that because it's a pointer which points to an NS object which is known in a linked list. And so basically you can just use your base pointer for that one and it would be fine. And it's only used for in comparison though, so as long as it's the right value, it's fine. It doesn't actually need to do anything with it. And then if that comparison is sound, and it should be the comparison should be what's expected to be, you end up going to this code, which holds the holy grail. And this is basically the jump to, so basically reference the A register and jump to that value. That's what you want. And if you get to that point, you have arbitrary code execution. This all sounds confusing and lots of pointers and all of this stuff, and you go like, well, fuck, that's going to take me forever to do. Turns out, so I wrote it all down, and I figured out that all of this stuff, you can make all of this stuff self-referencing, and basically all you need to do is have offsets. And so all you need is one simple base address, and you can have everything else point sort of to itself. If you work it out, which I did, kind of looks like this, and if you build up a structure like this, and so the base pointer is basically the pointer to your randomness object, right? So you need to know this one, and everything else you can just sort of make point to other places. And then, if you put C code right next to it, if you build it up like this, and you would put a pointer to that on the stack, and you do a format string bug, then this function pointer will get executed. That's pretty much how easy it is. So moving on to binary protocol handling. As I just mentioned, iOS apps use Objective-C, and Objective-C has pretty good classes to handle all sorts of strings and that kind of stuff. And if you stick to these classes, it's highly unlikely you'll have buffer overflows and all these low-level C-like security issues. There's one particular sort of instance where this isn't true, and if people start doing this in iOS apps, people have to fall back to C code, and that's where all the bad things happen, which is binary protocol handling. There are really no good classes to handle binary data in Objective-C, and when people start doing this, they fall back to C, and they end up using the integer overflows and integer sightness bugs and integer underflows, and mem copies that are abused, and all that kind of goodness pops right back up. I'm not really going to cover specifics of that because I would assume the audience knows. If you'd like to know more, I have a different set of slides which I built for a set of game developers who were not aware of this stuff, and where I've got a couple of slides specifically targeting binary protocol handling. But I would assume you would know about these things. But if not, ask me about it, and I can give you a set of slides that do contain this stuff. The other thing is that while these mobile OSs, they're all based on desktop or server OSs, and so they use the same file system or file system APIs. And so since iOS is based on Mac OS X, iOS ends up using Mac OS X file APIs, and specifically they use this NS File Manager class. And what's funny about if you just start using local file system stuff, you have to worry about directory traversals. And so this is pretty trivial stuff. And this is stuff I've seen in real applications, so this stuff really happens. Where people, they start to build up a path name, and part of the user data is attacker controlled, part of the file name, and then, use a temporary directory, and you open that file and you write to it. Obviously, trivial ... // is totally going to work. So if you're an iOS developer and you start using file APIs, be very, very careful if there's any attacker control data in the file path, because this stuff will bite you in the ass. Now, it gets better because they use all these strings are Objective-C strings, and they're not C strings. And as we know, C strings null terminate with a null byte, but Objective-C strings don't null terminate with a null byte. So when people go like, oh, we'll try to prevent this, people exploit this stuff where we'll append an extension, and nobody can, and because we have this extension, even if people do directory traversals, they won't be able to hit any interesting files. Except in Objective-C you can, because even though Objective-C doesn't see the terminating null byte as end of a string, once you get to the open system call, that one's written in C, and that one will see, oh, there's a 0 byte. Everything after 0 byte, I'll just discard. So that totally works, and instead of using ... you now have to use ... then say etc password, and then 0 bytes, right? And so the exact same thing holds true for Android, except now it's Java code instead of Objective-C code. So instead of using the iOS file APIs, you end up using the Java file APIs. And so just do new file name, the exact same thing works here. ... // works. Exact same thing for poison null bytes. Java strings are not like C strings at all. And so getting rid of, so you can have 0 bytes in there, and then add an extension to it, and then once you get to the C-level system calls, the extension sort of just goes away. So exact same issues affecting iOS as do Android. Next up is iOS's XML parser. They have this thing called NSXML parser. And NSXML parser is obviously used to handle XML data. It handles DDTs by default, so it's vulnerable to the billion laughs attacks. You can't turn this shit off. And the one thing you do have is it doesn't resolve external entities, but it will totally parse entities. So if you would feed it something like this, which is this sort of self-referencing doc type where you've got entities referencing entities, when this stuff gets expanded right here, you're going to need terabytes of memory, and obviously this is not going to work, and the app's going to sit there for a very long time trying to allocate all available memory and eventually blow up on an exception because it can't get all the memory it would need. Now, as I said, you can't turn it off, but there's sort of a workaround. The way NSXML parser works is that you have to define callbacks for every little thing you find. And there's 6 specific callbacks with DDTs, found element, declaration found, so-and-so, and there's basically 6. And so what you can do is, or what you should do is you should define every single one of these callbacks. And then if that callback ever gets hit, just bail out. Say, oh, you've got a DDT in there? Screw you, I'm not handling that shit. Just bail out. It works. It's kind of hairy. It's error-prone. Developers often sometimes forget stuff, and if you forget to declare any one of these, then it might still be possible. So hairy, error-prone. It should be easier. There should be a simple attribute in the NSXML parser object where you say, don't do DDTs. That would be ideal. Obviously, XML is often parsed recursively as well, and so obviously most XML handling code is vulnerable to this, and if you use NSXML in your iOS app, you have to be very careful here too, because if you see a tag and you see the same tag embedded in that tag, chances are you would end up calling the same parsing function, and then that's great, except if you've got 10,000 or 100,000 of these embedded tags, you end up blowing up the stack because there's a limited amount of stack space, and every time you call your function, you got to build up a stack frame. And so eventually you would end up with recursive stack overflow. Very, very common. Certainly in most XML parsers, very common. The way you fix this is you have a recursion limit. You say, if I see 100 embedded XML tags of the same name, something bad's up. There's no way that would ever happen. And so, once you get to 101, you say, you bail out and you say this is invalid XML. Now, since we're on the topic of XML, there's also obviously the possibility of having XML injection. Again, this is quite often when you're talking to web services and you use REST or SOAP or send JSON back and forth. There's a possibility of XML injection. Now, XML injection, again, XML injection isn't specific to mobile apps, but it is incredibly, incredibly common in mobile apps. Certainly on iOS and Android apps, I've seen quite a few of these. This obviously happens when a piece of attack control data is put inside of a request going from the client to the server, and it's not being properly encoded. So basically the idea is that if you start doing this, you better encode your XML data. And this is sort of an Android, this is, it's all trivial stuff, but it's basically sort of you build up the XML data, and then if the data from the get item is potentially attack controlled, you end up with XML injection right here. The iOS SDK comes with APIs to do SQL stuff because you can do client-side SQL and stuff. Obviously, this is pretty standard stuff. You start doing SQL, better be very careful with SQL injection. So this is a very, very trivial example where you open up a SQLite database, you do a select from the SQLite database, and this is a trivial SQL injection bug right here. So this is basically what it looks like, and SQLite is pretty good because it actually has APIs to bind values to. So you can have a placeholder here and then bind this one to the placeholder. So you should be using those APIs instead of having straight SQL injection. Pretty trivial stuff, but I figured I'd mention it because this stuff is still pretty common in mobile apps. Android, very similar. They have this thing called android.database.sqlite, which is basically the Android guys put a bunch of Java wrappers around the SQLite APIs. Again, the code that would be, so this vulnerable code, for example, is quite similar to the one I showed earlier, except now it's Java code instead of C code. So the first thing you do is you open up a SQL database, and then you execute a SQL statement, you say select from so-and-so, and if get username or get password is potentially attacker controlled, obviously you would end up with SQL injection. So, pretty trivial stuff, but it's there, and it's common that people kind of screw it up. I've got no more Android stuff. I've got one more iOS specific stuff. And this is sort of something I stumbled upon a few months ago when doing a security review of an iPhone app. And it's sort of, if you come from the Java world, you might know some of this stuff, but it's a type confusion attack. And what's interesting is that, so Objective-C has all these classes, NS URL connection, NS, so everything starts with NS, and that's because, well, NS I guess comes from next step, but it's because everything inherits, every object in Objective-C inherits from their base class, which is called NS object. And they have a catch-all type for this. So any object that you define, you can basically say it's of type ID. And then that means it's something that is either NS object or inherent from NS object. And so when you start using this ID catch-all class, you have catch-all name, you have to be really, really careful. Because even though it says ID, it could be a string or a dictionary or an array or a Boolean or an integer or any number of objects. And so you sort of, if you just take IDs as return values for functions, you kind of have to wonder what class is it. If you don't, you get hosed. And the reason why is because Objective-C is slightly different from other objective-oriented programming languages such as C++ and the like. Because what they do is they do the class names and method names get resolved in runtime. Earlier when I showed that Objective-C send message API, that guy takes care of a lot of this stuff. And so they use this message passing stuff where you can define method names in runtime, and they'll go look up what the actual function pointer is. And this stuff, the same thing happens for classes and class names and that kind of stuff. So basically, if you can take an arbitrary arbitrary object, which is ID, and you can call any method on it, and this Objective-C send message will go out and see if that method exists, and if that method name exists, it will call it on whatever class you're using, even though it just says it's of type ID. And so, for example, let's say you have a class called blah, and now with a method that's called object for key that calls an arbitrary function pointer. And now let's say you have some function that returns ID, and you assume it's a dictionary, and you call the object for key method on your dictionary, except it's not a dictionary, and it's really the blah blah class. And so you end up calling object for dictionary, which calls an arbitrary function pointer instead of returning an object for a key from a dictionary. And while it sounds a bit confusing, this stuff is actually very common. And the most common one I've seen is when people start parsing JSON. And particularly so there's a very, very common JSON library for iOS. It's called SBJSON. And that one basically overloads the string class and exports a few methods where if you call them, what it does is you pass in a string of JSON, it deserializes all the stuff, and returns you back an ID to the deserialized JSON stuff. And then generally what people do is they'll do something like, JSON string of JSON value, and what comes back is sort of, they say, this thing returns an ID value, and you say, oh, it's a dictionary, and then you just start calling arbitrary methods on your dictionary, which is wrong because this JSON deserializer doesn't have to return a dictionary. It can return an array, a string, a Boolean, and an integer. So even though you think it's a dictionary, it may very well not be a dictionary, depending on the JSON data that was sent through your application. This is actually incredibly common. So I went back and looked at all the apps I've looked at that did JSON deserialization with SBJSON. Every single app I've seen that uses JSON and SBJSON has been vulnerable to these kind of type confusion attacks. I haven't quite explored them as deep as I'd like to. I know bad things can happen. I know at the very least your app can crash. Depending on what you're doing, I would imagine there's code execution in there somewhere, but I haven't had the time yet to look at it in the amount of depth that I would have liked to. The way to fix this is kind of easy. All these, so NS objects or anything that is from NS object, there's a couple of classes that you have to implement. One of them is called isKindOfClass, and basically you say isKindOfClass, and then you give it the type of the class, and if it says true, then it's that kind of class. If it's not, then it's not that class. You should be calling methods for one particular class and this other class. So when you see this kind of code, before this dictionary ever gets used, you should be calling a kind of class to make sure something is a dictionary. Yeah, that's it. About 10 minutes worth of question time. If anyone has any questions.